Hey everyone, welcome to the online meetup. It's Royston Lobo here, Senior Technical Architect working at MuleSoft. Just while we're waiting to begin, I wanted to announce that you can register for Connect, which is our online digital conference. Registrations are open and it's free. There are different dates for each region, so please feel free to register at a time that's convenient for you. Vitaly, if you can go to the next slide, please. Today we have Vitaly Mikitenko from our support team based out of Sydney, who's going to be talking to us about some of the advanced troubleshooting techniques for application performance. So if you've got questions, please use the YouTube chat to ask them, and I will be asking questions on your behalf later on in the presentation. So Vitaly, when you're ready, please begin.
Yep, thank you so much, Royston. Hello, everyone. Thank you so much for joining this online meetup. Today, we're going to talk about the advanced troubleshooting of application performance in regards to Mule4 application, Mule4, and let's move on. So first of all, a little bit about myself. I'm a senior custom architect working for JVM support team, having more than 20 years of experience in IT. More than 5 years I spent working with heavily loaded integration platforms, processing tens of billions of records daily. Working for MuleSoft since 2017, and my specialty is performance and reliability troubleshooting. What's covered in this presentation? We'll talk a little bit about the basics like Java virtual machine memory distribution. We'll cover some top level related to troubleshooting information in regards to Mule4 execution engine. And we consider the importance and why we need thread dumps and heap dumps in order to have the full picture when troubleshooting application problems. We also will talk about how we get applications ready, or how we do a proactive troubleshooting when deploying applications to CloudHub and on-premise. We will discuss some tool set we use on a daily basis. Some commands might be very familiar for you, but some of them and the way we use them could be something new for you. I'd really appreciate the feedback, and we will have some demo with some troubleshooting scenarios. Okay, what's next? Let's talk about Mule4 memory and threading. First of all, let's discuss how JVM memory is distributed. Many people, when they talk about Java memory, they usually talk about Heap. On the left side of this presentation slide, you may find the typical JVM memory distribution. As it appears, the JVM memory is not only a part of the heap, but let's go one by one. So typical scenario for JVM memory distribution, you have like 1 GB of heap memory allocated, which is split between all the new generation half-half. But apart from that, you have native memory consumers or allocations, which are variable in size. You have meta space, and by default, it's around 256 megabytes. You have thread stack, where every Java thread creates a thread stack of 1 megabyte. So for a typical application running on 1 gigabyte runtime with 160, 180 threads, it would give us a consumption of 100 up to 180 megabytes of memory, but it depends on the real use case scenario, of course. You also have a code cache, which using default JVM parameters can grow up to the 240 megabytes. The value can be adjusted, and those values are dynamically allocated. So when code cache does not require that memory, it reclaims back memory to the operating system. You also have internal memory allocation, or how we know it from the logs, it's called direct memory. Mostly it's used for network input-output and streaming. The tricky part with internal memory allocation, that if not limited, it can grow up to the size of heap using JVM defaults. Doesn't matter if it's Oracle JDK or OpenJDK. And you have some other memory consumers, native memory consumers, which we can just mention, but they don't make much trouble to us as they don't consume a lot of memory. On the right side of this slide, you can find, for example, a typical scenario of the application deployed to 1 GB runtime with some allocations as presented. For example, Java Heap consumes 1 GB. Class, which corresponds to meta space, consumes 153 megabytes. Threads, as I mentioned to you before, 1 megabyte per every thread stack, 93 megabytes, which means that we have around 90 threads running in JVM. Code cache, garbage collector, and internal memory allocation, which we should pay attention to. The tricky part, for example, with the variable internal memory allocation, that using different tools for memory monitoring, you won't find that allocation there. You need to explicitly enable native memory tracking to have this reported. We will consider it later during the troubleshooting exercise. Let's move to the next slide. Sorry, let me come back for a second. So as you can see, if we talk about runtime memory or JVM memory, we should always consider that as a thumb rule, we always need to reserve at least 50% of memory available for native memory allocations which are on top of heap. So having a, let's say, 1 GB of heap allocated, it's a good thing to have at least 2 GB of memory allocated for the virtual machine we are running runtime in. So let's move to Mule execution engine. So unlike Mule 3, which had dedicated threading profiles for different types of connectors, workers, Mule 4 has very strict rules in terms of threads, their types, and what can be executed on a particular thread type. And also those thread numbers are limited. Technically, on a high level, you have CPU-like threads, which are calculated as 2 times number of cores. And for example, HTTP requests or Mule logger are working using those threads. You have CPU-intensive threads, which used for very heavy operations. The best example here would be DataViv, which makes transformation. It literally always executes on CPU-intensive threads, and you have the same formula for allocating those. And you have a number of IO blocking threads, which are used for blocking operations, whether it's a file read, write, or database operation. It would use IO blocking thread. What thread to use are predefined by event processors. And also, if you talk about the custom extensions, or how we call them, custom modules, it's a part of the Mule SDK, which predefines which thread this or another type of processing can use. The scheduler pools for threading can be modified using the file located at configuration folder of Mule runtime. The extract of that file is presented on the right side of the screen. So as you can see, formulas for CPU light, CPU intensive, and IO threads. IO threads, the number of IO threads is calculated based on the allocated heap. So mem variable here stands for heap. So for example, a typical scenario for 0.1 we call CloudHub worker, you would have like 45, 48 IO threads and 4 threads for CPU light and 4 threads for CPU intensive processing. These parameters are not configurable in CloudHub, but they can be adjusted in on-prem installations. What's also important here that when you troubleshoot the application and then examine logs, the thread type can be found in the logged messages, like here. And you would ask probably what the problem with the limited number of threads. On one hand, you don't have thread leaks, which is good, like it used to be in Mule 3 if the application was misconfigured. But if the load to the application is too high or the runtime is not configured properly, you would face a problem of flowback pressure, which happens under extremely heavy load when the flow cannot accept any new messages. And in terms of HTTP listener, for example, it would respond back with 503. Let's move on. And let's talk about dumps we use to troubleshoot applications. First of all, let's talk about the thread dump. Thread dump, or if you want to rephrase it, it's the snapshot of the current execution state. So if we want to know what the runtime was doing, what every single thread was doing at any moment of time, we take a thread dump. That thread dump allows us to analyze based on the thread stack to see at what module, for example, the application got stuck. We can see if the thread was blocked or not. We can see, because we have a limited number of threads for CPU light and CPU intensive, something might block the execution. And you take a thread dump and you can find that, for example, all CPU light threads are blocked. So examining the thread stack, you can figure out to what application it belongs, because in the thread stack, you have the application name, flow name, and thread type executed. And it also allows, in conjunction with other tools, to identify, for example, the CPU consuming thread, and identify some patterns for problems. If thread dump, it's a snapshot of the current execution state. The heap dump, it's a snapshot of the current heap state. So basically, it dumps all the heap memory at a moment of time. And then you can use different tool set like JVM for roughly estimating using histogram, or Eclipse Memory Analyzer to generate reports, or use object query language, which is a very powerful tool to find something very, very well hidden inside the heap. Let's move on. So how we get applications ready for different types of deployments. In this presentation, we cover CloudHub and on-premise, but all the discussed here is applicable to other types of deployments, like runtime fabric, for example. Let's move on. So when we deploy applications to CloudHub, usually what we experience is a typical reported scenario is an application works perfectly in Endpoint Studio, but when it's deployed to CloudHub and it starts accepting the load, it becomes unresponsive or restarts. For example, or when we do a capacity planning exercise, we think sometimes that it's because one VCore worker, for example, has more memory, it can process more messages per single moment of time, for example. And we think that one VCore worker would be better than deploying application, for example, to 5 0.2 VCores. So, and also, we usually face challenges when we do load testing of applications in CloudHub. Or, for example, the application was working fine locally, did not cause any issues. We deployed to CloudHub, and we noticed an error in logs, like no space left on device, because CloudHub has limited resources. Let's talk about this as well. And also, let's talk about logging in CloudHub. I think it's a very important topic, because the logging has negative impact on any type of deployment, but in particular to fractional VCore workers. Before we move forward, let's understand why applications try to understand why applications fail in CloudHub but work good locally. So first of all, when people talk about the memory and memory consumed by the application, usually they run the top command. They look at the residential memory occupation, like on the screenshot here, which is 723 megabytes, and they think why the application failed if it was consuming only 723 megabytes when we have 1 gigabyte of total memory available. The thing is that only specific system processes in modern operating systems are actually using direct memory allocation from residential memory. The rest of processes are working in its own virtual address space. And you can allocate more memory than is available in a virtual address space. For example, if you have a look at this screenshot once again, you can find here the column called virt. And this column represents how much memory this process can address on 1 gigabyte of physical memory. Usually, if you talk about Linux kernel, for example, this parameter, it's a heuristic parameter predefined by the OS kernel formulas. And when the process starts, kernel just assumes that this process might address up to 3 gigabytes of virtual address space in system. And it defines it like this. So every process, apart from that, having virtual address space for every single process, every process can work and address the same memory addresses. For example, JVM process can start addressing memory pages starting from address 0, and some system process can start addressing memory pages from 0. If you ask, how does it work with the physical memory? On a very high level, operating system and memory management unit of operating system has a specific table which does the mapping, magical mapping between virtual address space and space, as presented on this screenshot on the right side. For example, as you can see, memory pages which are aligned in JVM process, but they are actually stored at different locations in physical memory. So the same for process X, for example. And here is the mapping. And some memory pages can be stored in swap. So, and because swap is a part of the virtual address space, this allows processes to allocate actually more memory than the available physical memory. In fact, processes can allocate more memory, try to allocate, even there is no swap, because they still work in the virtual address space, but that could lead to some bad consequences. But let's ask ourselves, if I add large swap file, does it mean I can process more or larger payload using that kind of hardware configuration? The answer would be yes and no, and depends on a real use case scenario. Let's move to the next slide, and I'll explain why. So having less memory working and processing payloads, you fragment the application or JVM or any other process in the system. It basically fragments the memory. As we remember from a previous slide, the physical location of memory pages belonging to some process can vary and can be distributed throughout the whole operating system memory available. So what happens is, let's consider one scenario for simple hello world application processing some not that large payloads. So the application is listening for HTTP request. It accepts the first request with the payload of occupying 3 abstract memory pages. It starts processing it, doing some, let's say, data weave transformation. While it's being processed, the second request comes to the application, and it requires 2 memory pages. While those 2 requests are being processed in parallel using different threads, the request number 3 arrives to the system with 4 memory pages allocated. By the time we receive the 4th request, the first request, which was the second request, which was relatively small, has been processed, and response was sent back to the requester. So the memory pages were freed. And then we get the 4th request while we still have the first and the 3rd request in memory. And the 4th request has the biggest payload with requiring 6 abstract memory pages. We would ask ourselves, we have 1, 2, plus 5, 7 memory pages. We should be fine, right? But if you take a look at the log of this abstract application, we would find something like on the screenshot on top of the screen, top right part of the screen. The application failed, not being able to allocate only 12 kilobytes of memory. So what happened is, basically, let's assume all those payloads required active memory pages. So it was active processing. And because of that, this answers basically, because of that, those pages could not be stored in swap memory, because swap accepts only inactive memory pages. And the application was not being able to allocate those 6 pages straight away. The memory management unit took some time to defragment the memory and allocate it. Memory management unit, because all the memory pages were active, could not move some pages back and forth and allocate unfragmented 6 memory pages. The application failed. So to answer the question, if I allocate more swap, would I be able to process more or not? It depends on the size of the payload, on the on the rate of the messages to process. So, for example, if an operating system decides that these memory pages are inactive for this moment of time, it can swap them out. If they are active, they can't be swapped out. A good typical live scenario, for example, you have a drawer next to your table, and you have a laptop there stored. So technically, you have a free table out of all stuff, and you have plenty of room. But in order to start working on your laptop, you need to make it active. You need to take it out of the drawer, put it on a table, and open the lid, right? Similar with memory pages. So until your drawer is in, until your laptop is in the drawer, it's inactive. For example, how to see some statistics about swapping and confirm that we have, for example, huge memory fragmentation and memory pages are being defragmented and moved back and forth. If you run a SAR command, which is a part of the CStat package, we can, with -D parameter, we would find there are 2 columns, like faults and major faults per second. At this moment of time, for example, the application, the Linux kernel was not able to allocate 2063 something memory pages per second. One memory page is 4 kilobytes of size. So it means that the defragmentation of memory happens in the operating system non-stop. And it's a normal process. Don't be afraid of that. But you need to have an insurance which would allow you, if you're not able to allocate or defragment the memory, like on the scenario here, without accessing swap, you need to have an insurance, which is swap, to move inactive memory pages, to swap them out temporarily, and then swap in back to the memory when those memory pages are required by some process or application. And we need to consider that any swapping, especially intensive swapping, leads to performance degradation. So we need to carefully size our application runtimes. We need to size application virtual machines when they deploy on-prem, and we need to take all those parameters into consideration. And this type of fragmentation is called external memory fragmentation. Apart from that, there is an internal memory fragmentation, which is less relevant here, but still we need to know about it. For example, payload 1, it allocated 3 memory pages, but not because the payload was of, let's say, 12 kilobytes of size, but because probably it was of 9 kilobytes of size. So it still allocates 3 memory pages, but some part of that memory page, of the third memory page, will be free, and it can be used by other payload. That's why it's another overhead here, which leads to the difference in values. For example, when we check the size of the payload, it's 9 kilobytes, but we see that it requires actually 12 kilobytes of memory to process on a low level. So, and because CloudHub Worker has only a limited amount of memory, the defragmentation part by memory management happens more frequently, and it has less room for defragmentation. You run the same application with the same memory parameters in Studio, and it works perfectly. But the problem is that your working laptop with the Studio has, for example, 16 gigabytes of memory. Therefore, instead of having 1 or 2 or 4 gigabytes of memory, like on some application workers in CloudHub, you have lots of room to do memory movement without even accessing the swap. But in CloudHub, it's different. So this needs to be carefully considered, and I'll show you a way how you can at least have an estimate or simulate this behavior in CloudHub on some next slides. Let's move on. So apart from memory fragmentation, we also, coming back to native memory allocations, we need to consider that some of them can cause us issues if we don't limit them on purpose or if we don't consider them. Let's say we deploy the application to in Studio, we test it with 1 gigabyte of heap allocated. It's working perfectly, process data very fast, but it processes huge enormous amount of requests. But we deploy the CloudHub and the application starts failing. It restarts the worker, it's failing, it's restarting. So we take a heap dump because we suspect there could be probably a memory leak. We take a heap dump, generate a leak suspect report. The report says us no leaks found, and you don't know what to do. But then, after checking this presentation, watching this presentation, we know that we can enable, for example, native memory tracking for the application. And we can then, using JCMD command, print native memory occupiers. And under heavy load, we find that, for example, internal memory allocation committed literally 1 gigabyte of space in memory. So the total memory occupied by JVM with 1 gigabyte, only 1 gigabyte of heap memory, was around 2.5 gigabytes. Of course, this is the scenario for crashing when you have little room for defragmentation and active memory a defragmentation of memory without using swap. So this needs to be considered as well. So there is a way how we can at least roughly estimate if our application suits this or another type of worker in CloudHub, size of worker. You can, the easiest part is just to add some memory parameters here in the run configurations when you start your project, when you deploy your project. For example, parameters like on the screenshot here, they correspond to 0.1 vCore worker. You have around 490, 480 megabytes of heap. You enable native memory tracking. And if you enabled native memory tracking and you found the scenario similar to this one, you then try to limit native memory tracking. 32 megabytes, it's the limit. It's explained in the links in the knowledge article or available at our help portal. But 0.1, for example, has a limit of direct memory of 32 megabytes, just to prevent the worker from auto restarting. So if you run with these parameters the application, you can at least figure out if it's suitable to run on 0.1 or not, or you need something larger. If you want to go deeper and simulate with more precisely, you can go and modify the scheduler pools of the embedded runtime. So for example, if a laptop has 2 physical cores or 4 hyper-threading cores, I'm changing the coefficient from 2 to 1, and it will give me 4 CPU light and 4 CPU intensive threads. And this formula, because it's using heap memory, it will calculate me the number of IO threads similar to 0.1 vCore worker. So this way, I will have more or less full picture how my application might behave in CloudHub. However, it does not consider everything because, for example, fractional vCore workers, they have burstable resources. And it doesn't consider, it still does not consider memory fragmentation because you have still lots of memory for native memory defragmentation on top of the heap. It does not consider limited disk space in CloudHub, and it, let's say, does not consider in full the impact of logging. So when we are getting applications ready for CloudHub deployment, the recommendation would be to try and simulate with the heap allocation and threading profile. We also would try to track the native memory consumption and understand how much our application actually requires, and probably this or another type of worker will not be able to meet the requirements. This would probably give us an idea. For example, some custom Java module, custom compression component, for example, it uses an IO buffer for compression, and probably it does not use streaming and tries to allocate too large buffer in direct memory. That leads to the problem. So if we tune that custom module so it makes the streaming available, we probably will keep up with the same 0.1 vCore worker after that, and even before deploying to CloudHub. We also need to consider limited disk free space. Fractional vCore workers like 0.1, 0.2, they have around 5 gigabytes of free space when the application is deployed. So if you have, for example, an application which pulls files using SFTP protocol, does some magic transformation and pulls somewhere, and it temporarily stores them on an application worker, you need to understand that you cannot pull too many files in parallel. So probably to adjust concurrency for the application. So and make sure the current file is being deleted before the next is downloaded from the source. One of the knowledge articles in the links below explains how we can adaptively change the login for applications on not even restarting the application in CloudHub. So production applications should have very limited login. The login has performance impact, and that impact sometimes can be severe. If, for example, an application processes some SOAP requests and the size of the SOAP payload around 15 megabytes of size, you will end up with, let's say, 10 SOAP messages in logs. If you print the full payload in the logs, 10 messages in logs stored and nothing else. So one log file would contain only one message. And that makes impossible to troubleshoot application also. Plus, the time required to actually to print the payload in the log, you actually need some CPU resources. So it puts like huge overhead on this. Better to have the login adaptive, so you have at least two login levels for production deployment with info level and debug level, and you need to troubleshoot the problem. And to answer the question, what's better, deploy an application to 1 week coworker or to 5 0.2 week coworkers? We need to consider the combination and every single one of those, like payload size and processing intensity. If I have like small payloads, and usually the payload processing takes very, very little time, I'd say, but the rate of those messages is intense, probably 0.2 times 5 week coworkers would be a better option than 1 week core. Because at the very end of the day, if you don't consume much CPU, you have more processing threads. The number of CPU cores on 0.1, 0.2, and 1 week core is the same. The problem is that fractional week coworkers, they cannot utilize 100% of time, 100% of CPU. And that's where, for example, if you have large payloads with less rate, probably by testing and load testing, it's better to deploy to 1 week coworker and be happy with this solution. But if you have small payloads, but those payloads have some simple data with transformation, which does not consume too much CPU, but the rate of those messages is high, having the same money spent on workers, you would have the much better throughput using 0.2 week coworker as a thumb rule. Also, doing a load testing in CloudHub on fractional week coworkers, please never forget about the burstable CPU, that you cannot utilize a worker 100% of CPU non-stop. Usually, fractional week coworker fractional week coworkers, they are most suitable for the scenarios I explained, which are not very CPU consuming, with smaller payloads than the scenario when you want to process, I don't know, 50 megabyte payload with the 10 transactions per second. This would consume for sure all CPU resources available. So please don't get surprised when you do a load testing for the half of the day on fractional week coworker. You will get different results to what you were trying to test locally. Let's talk a bit about on-prem before we move to the next part. So when we deploy applications to on-premise, we have a little bit different challenges. So the one of them is resource allocation. How much memory should we allocate for the runtime? How much CPU cores we need to allocate? Because usually the typical scenario, a customer creates a virtual machine and allocates some resources to install the runtime there. Sometimes we forget about operating system limits, like the number of processes and open file descriptors. Needless to say, on a Linux level, a process and a thread are treated equally. So yes, our runtime has only one processing operating system, but it may have on-prem 5,000 to 6,000 threads. And if your operating system limit for processes is only 1000, your application will start failing. Also, open file descriptors, especially on some types of configurations. We will discuss about it. The challenge also is to estimate the number of applications to deploy per runtime. We also face stuff like gradual performance degradation within the time. We deploy more and more applications, the application starts working worse and worse. And sometimes when the on-prem installations have an issue when they have slow supportability because due to some reason, Java runtime environment was installed instead of JDK. And using JDK, you're not able to take a heap dump. You don't have all those tools and utilities which allow you to troubleshoot. And plus, sometimes we miss or we have lack of additional tools for supporting or even analyzing ourselves the applications. So when we create, install, configure the on-premise runtime, let's consider in the previous slides, let's keep the proportion of memory allocated for the heap, like 50-50, 50% of memory for heap, the rest for native memory allocations. But it can be different if you allocate a virtual machine of a considerably large size, let's say 32 gigabytes, 64 gigabytes. On a 64 gigabyte virtual machine, you probably don't need to allocate 32 gigabytes of heap, depending on the number of applications deployed, but still, the value should be different. So, and please don't forget to change the default values in the wrapper.conf, because default is 1 gigabyte of heap allocated, and then with 20 applications deployed, you'll for sure notice at least high CPU utilization by garbage collection. Because it's Mule4 and we have a limited number of threads, which are calculated based on the available resources allocated for the machine, we need to fine-tune the scheduler pools. If we, due to license restrictions, we allocate 32 gigabyte machine with 1 CPU core, it means that for all the applications deployed to 16 gigabytes of heap, and I would assume it's like 50, 60, 70 applications, you would have only 2 CPU intensive and 2 CPU light threads by default. This would result in at least mule flow back pressure. And default parameters for threading profile for scheduler pools should be changed. But there is no formula which suits everybody. It needs to be carefully chosen after completing the performance impact and capacity planning exercises. So also don't forget about limits, operating system limits. 2 most important limits, number of open files and number of processes. The recommended value for on-prem deployments is around 65,000 for both. It's like a thumb rule, but let's assume, for example, Hello World application on a standalone runtime, you would have around, just deploy an application, you would have around 1,600 open files and around 100 threads. So yeah, and sometimes the challenge here is that people usually, they created a user, let's say Mule on the Unix operating system, and they check the limits with ulimit -a command, and it shows everything's fine. We have 65,000, but then they deploy an application, and the application reports too many open files in logs. Then, when you check with another command, which shows the actual parameters applied, we see there are different values which led to that situation. We will discuss it later during the exercise. So, taking into account the swap, it's a good idea first to allocate the swap always, even if we deploy to some cloud instance and by default it doesn't have any page file allocated. But also, if you don't want to make swapping too intense and causes performance degradations, you probably need to fine-tune sloppiness parameter. You can find lots of information in the internet or at kernel.org website, but basically you can control at what threshold of memory utilization the operating system starts swapping. Number of applications per runtime. Consider that it's a good idea to have around 20, 25 applications deployed per runtime. The hard limit is 200, but with 200 applications deployment, you have very little supportability of that environment. It's literally impossible to troubleshoot if some application causes an issue. Another story here, if something goes wrong, you need to restart the whole runtime and the whole 200 applications, which is not good. Also, it's a very good to recommend verbose, the heap dump generation on out of memory era. It would allow you to understand what was wrong when by the time the runtime crashed. Yeah, again, even if it's a non-prem deployment, consider adjusting login levels and have 2 login levels for info and debug level. As a third party provided by MuleSoft tool for troubleshooting and collecting debug data, we'd recommend to use support information collector. It's not only to raise cases with MuleSoft support, but also to analyze yourself. Instead of going to different system views, different configuration files, it does a magic for you. It creates an archive which can be then extracted, downloaded, and analyzed in a very good way. And not only for that purposes, there is a knowledge article again in the links which describes all the functionality of the collector. Some tool set we use to troubleshoot application. Sorry for the typo. So first of all, it's CLI commands provided by JDK, JStack for example, thread dump generation, JMap for taking heap dumps and histograms of the live runtime process. As mentioned before, heap dump on out of memory, native memory tracking, and commands to use it. Preventive garbage collections on a live process, which I'll show you where it's useful. For example, if you want to estimate if you have a thread leak, if you have a heap leak or not. Garbage collection statistics for a certain period of time. You see on-prem runtime, it starts with more and more applications deployed, with more and more load going through the runtime and applications deployed. You see that it consumes more and more CPU, but that consumption of CPU is not one-to-one matched with the load increase. So if you enable garbage collection, you might find that your runtime does the garbage collection non-stop. It defragments the memory, it moves memory pages, it removes all the objects, etc. So, and it has a huge performance overhead. Probably it's time to resize your runtime, and not only resize, but maybe probably to add some CPU cores. And JPS, Java process list, similar to PS command, but for Java processes. Let's move to Linux tools. First of all, the most popular one is stop. And there are some parameters in this command which allow you to, in conjunction with the thread dump, to identify the CPU consuming thread. I'll show you later. Watch, very good utility, for example, to use in paired with some other, for example, native memory tracking. You can do it like in a top monitoring way. SAR or VMstat, extremely powerful packages. VMstat is supplied with operating system. SAR needs to be installed. It's a part of the system package. You can collect statistics of memory consumption, swapping, memory utilization, etc., etc., etc. There is a whole bunch of different metrics can be collected using those. Not only that, but it also stores the data by default for the last 30 days, which is very useful. Some LSOF, list of open files, to check if you have a file descriptor leak, or to check how many network connections are opened for a particular process or for a particular user. Very useful. In terms of why I'm using this dollar parenthesis PID of Java, it just returns the process ID of Java process, this expression. Another useful command. The only caveat here, you need to have one Java process on a virtual machine. Otherwise, it will not work. So some system views which allow you to roughly, not only roughly, but estimate and see the hardware configuration of the machine you are working on. If you do cat proc mem info, you will find something like here. And as you can see, on a 1 GB machine, you can address using malloc system call up to, I don't know, 32 terabytes, I believe, of memory. This is the difference between virtual and residential memory. Plus, you can see how many memory pages you have active, inactive, how many pages are swapped out, etc., etc., etc. Proc CPU info will show you what kind of CPU model you have and how many cores. Limits to check, it's the proper way, I would say, to check if proper system limits for processes and open file descriptors are applied to the runtime. Status, it's a snapshot of the current state of the memory and memory utilized and CPU. For example, VM high watermark stands for the highest residential memory utilized by the application at some moment of time. The current residential memory occupation and how much of the particular process are swapped out. And of course, the number of threads. You don't need even to take a thread dump to estimate in 1 second how many threads are running on the application, whether you have a thread leak or not. Net start to check open ports, and native thread dump generation with one very useful addition in Linux. It's kill death 3, which generates a native thread dump. And I'll show you how you can use it apart from the thread dump. It's safe operation, does not restart the runtime. It just sends the search system signal to JVM process, and JVM process, when it receives, it generates a thread dump in mule_ee.log file. So, and some GUI and CLI tools, which are JConsole, very powerful tool for graphical representation of what we have all discussed. It's supplied with JDK. You don't need to download and install it. You already have it. Eclipse memory analyzing tool, very handy for heap analysis. Also, there are third-party tools like VisualVM, Yoki, load testing tools like JMeter, if you want to build something robust, complex, or Heap for more simple way of testing. The screenshot is provided on the right, but it has a very good representation of even prints a histogram with the response times and how many requests failed, how many processed, etc. And of course, CURL, which allows you to send requests and receive responses for some application testing. Let's have some troubleshooting exercise. So we have a virtual machine configured with 1 GB of memory, 50% of memory allocated for heap, some tiny swap partition. And let me show you some basic troubleshooting steps you can take when you deploy your application. So let's start from sanity checks, which you can take to troubleshoot the application. Apologies. I'll probably need to make it a little bit. Okay. So, for example, we want to understand what we are dealing with, what kind of virtual machine it is. First of all, let me log into Mule user. Oh, sorry. Then, for example, we want to check what it is, what the machine is, because maybe Vitaly is saying something wrong. We print mem info, and we see memory total 1 GB. Free memory we have 64 megabytes and available 34. And this is a very good indication, by the way. This particular virtual machine was configured exactly to have shortage of resources. And as you can see, if you print, for example, with the free command, it will show you 64 megabytes available, 66, whatever, more or less. But actually, you have 34. And this is basically the only way to see this value. Why it happens? Because the kernel of the operating system has some predefined memory allocations which it does not allow to use. You can also see how much slop is utilized, again, in active memory pages. So let's move on and check our regular ps-ef grep Java. This is our runtime running, right? So we want to check whether our operating system limits are configured properly. I can see that, for example, I have max processes defined as 3,700, open files 10,240, so more or less fine. At this particular runtime, it's equal, but sometimes you can face a different scenario. For example, if the Linux service was created and in a custom way, custom script, and it does not correctly inherit or propagate the limits of the user, because all the services, they start on the root user, and then the process itself starts on the user we define, operating system user we define. So in this way, if it's not configured properly, you can face a situation when system limits of the underlying root user were taken into account. And root user by default has, for example, open files limit 1024. That's where your application will fail. So running this view, you can estimate if everything's fine with your runtime or not. These two guys. Again, status, one of my favorite ones, which prints the current state or snapshot of the current state for the Java process. And as you can see, at some moment of time, the residential memory allocation was 864 megabytes. At the moment, it allocates 768, so the load dropped. But also we see that 100 megabytes are in swap, and our application is running with 96 threads, which is fine for around 500 heap allocated, more or less fine from Mule4. So as you can see, just running this command, I already can check the health of the Java process, and in a very good way. For example, the same SAR command, I can see what CPU utilization I used to have and estimate if something goes wrong or some different parameters as well here. So let's do an interesting exercise, and let's identify a CPU consuming thread. For example, we have an on-prem deployment with 50 applications, and we see the huge CPU load. But knowing that we have 50 applications deployed, it's very tricky to understand what application is causing an issue, what flow in that particular application is causing an issue. So let's try and figure it out. Let's log in. I will use here the top command with -H parameter. Why? Because it will print me not only processes, but threads. And I will use the Hey utility to send 10,000 requests with rate limit of 10 requests per second.
Excuse me, Vitaly.
So
is it possible
yes.
to increase the font size on your terminal? if it's not too much trouble.
Yeah, sorry for this. Let me see if I can do it. Buffer. Show session. Let me see. Yeah, hold on a second. Let me check.
You could try Command plus. I think that works for me.
Command plus. Yeah. Oh yeah. Sorry guys. Thank you for letting me know. So okay, let's run it again. Sorry for this interruption. This Docker. No. Let me find this. Yeah. So let's send a load to the application. This is our top command plus. Yeah, this is our plus, and we can see that there are at least 3 threads which occupy utilizing the CPU. We'll have this thread ID here, which is 53, 39, 54, sorry, 54, 39. We will convert it to hexadecimal, and we will take a native thread dump. Go to mule folder. Logs. This file. And it was 153F. Let's search for 153F. Okay. Yeah, this one. So was presented on one of the slides. I didn't mention it, that process ID from top output is presented in the thread dump as NID, but in hexadecimal format. So checking, for example, top output with -H, you can find the process ID converted to hexadecimal, then take a thread dump and find that, for example, this particular thread of the Hello World CPU application in this Hello World CPU thread flow using CPU intensive thread was doing some database CSV processing and causing us a headache, preventing other applications from working properly. So if we then open the application, we will find here the flow. And in that flow, we will find, for example, a data weave transformation, which basically does our CSV processing, converting CSV to JSON, which consumes some CPU. Okay, so what's next? So let's also, yeah. So let's see how usually I'm, for example, doing the native memory tracking. Okay. Native memory tracking. So I have native memory tracking configured in my wrapper.conf. Heap dump out of memory. Yeah. So I have native memory tracking here configured, right? So if I do jcmd of Java pc.run, sorry, not this one. Yeah. Memory. I will find the full output here. So my virtual machine JVM with 500 megabytes almost of heap allocated actually consumes from residential memory around 950 megabytes. And then we check, for example, we have on the processing 97 threads. Every thread stack is around exactly 1 megabyte by default. And then we check code cache not relevant here, and we see, for example, only internal memory allocation was 165 megabytes. So probably this application would have some issues when deployed to CloudHub, if not changed. Sorry, this one is screaming. We'll close it. Java status. And we can find here that our JVM process, sorry, here, 128 megabytes are swapped out. Inactive memory pages, of course. So, and for example, if I want to quickly estimate my heap object allocations, I can use this command gmap-histo of Java. This would give me an idea should I take a heap dump or not, but because taking a heap dump it's more lengthy process, this command can be executed much faster. To print a histogram, and I can see that something is occupying 25 megabytes plus some another object byte array, 20 megabytes. It's not a big deal. If we start, for example, the processing here again, we will find different numbers here. Yeah, you see, it started growing. It started growing, but if it drops down, if we save, if not, we're not safe. It's better to take a heap dump. And how we take a heap dump, for example, yeah. So to take a heap dump, we will use the same jmap dump, part of the present format, b file heap meetup, for example. And here we do this one. And this is our heap dump. Then we can zip it, download, and analyze. For example, this particular application can generate a heap dump like this one. Command plus, yeah, doesn't work, sorry. This Java application, it's Eclipse Memory Analyzer. I took a heap dump from this application before, just to save time, and I found that some object allocates 300 megabytes of memory. After generating a leak suspect report, I can find that one instance of partitioned in memory object store actually consumes 300 megabytes, which is not good. We will go back to the application here, and we might find here cache configured. And cache had a misconfiguration. Cache had a misconfiguration with the object store TTL and expiration interval. So regardless of, for example, number of entries and TTL of 2 minutes, the expiration job was running every 24 hours, which led to actual growth uncontrolled of the object store. And that's how I can, for example, identify and figure out probably there need to be some changes in the configuration. Let's show me you some other stuff. The last one, I believe. So for today, yeah. So heap dump I showed you, and let's do a graph. I mentioned you before that native thread dump is very useful feature. So sometimes to understand if your application has some leak, memory leak, it's very good to have a rough estimate, not only using JMap histogram or taking a heap dump, but also to, for example, to do a garbage collection and see if objects are evicted from heap or not. So we have now the application running with some load, adding objects to object store. If you do JMap history of Java, we will find that more and more memory. Oh, too much. Sorry. Like -20 would be enough. Yeah. So as we can see, the size of the objects in the heap is growing. So we can take a native thread dump, of Java. Sorry for keep you waiting. We have almost finished. Then using JCMD again, of Java. Forgot to mention, it's safe to execute those commands on a live environment. They don't usually cause any problems. And then we take the native thread dump again after garbage collection generation. So JCMD gc.run did a full garbage collection. We have a native thread dump before garbage collection, and and we do a thread dump after garbage collection. We are in logs folder, and we can, for example, do this command. And let's consider two last values because I was executing those commands before. And we can see, for example, this application has a leak. The new generation area before garbage collection consumed 142 megabytes. After garbage collection, it started consuming 100 megabytes. But the old generation area before and after literally hasn't changed in size occupied. 7 kilobytes, it's not something. So, okay, there is a problem. There is a leak, probably in the application configuration like I showed you in Studio. That's where you start digging and understanding. So apart from that, this is very useful for native thread dump because you can see actually the meta space occupied. And yeah, if you have or not a leak there as well. And if we want to see how does it look like inside the Muley file, it's basically a thread dump plus some very valuable addition at the bottom. So you can see CSV, yeah, for example, the thread which is consuming CPU intensive thread pool and processing CSV, etc., etc., etc. That's it for today. Thank you so much for listening, and I hope it was helpful for you, and hope you will have some better knowledge how you can troubleshoot your application yourself before you raise a support ticket with us. Thank you so much for listening. You also, sorry, I forgot to mention a couple slides. You will also find here the links which I mentioned before, used to get this presentation ready. Use of documentation, help center with knowledge articles and some other links like JDK documentation. And that's it. Please feel free to ask your questions. Thank you so much.
Hey, Vitaly, thank you very much for your presentation. I have a question from the chat. The question is for a hold on. Can we connect to CloudHub Worker using Java tools?
It's not supported. Sorry, due to security reasons. Yeah, I've heard. Thank you so much. Good question, but unfortunately.
Thank you.
Sorry.
You broke up over there, but from what I heard, it's not supported due to.
Yeah, let me repeat it because sorry for some connectivity issue at my end. If I'm not breaking up now, so basically it's not supported due to security concerns. The less ports you have open in CloudHub, the less vulnerabilities you have. So, yeah, next question.
Thank you. There was a question earlier about default thread pools for a 0.2 we call CloudHub Worker. Any comments around that?
Yeah, so except IO pool, you have the same number of CPU intensive and CPU light threads. 0.1, 0.2, and 1 week workers. Technically, they all have 2 CPU cores. The difference is that fractional week workers, they cannot use those CPU cores for a long period of time. I hope this answers the question.
Thank you. There was a question about describing some of the benefits of the tools you've shown today. Maybe with that question, you could also give some input. If someone is operating on a Windows environment, what sort of tooling is available to them from your experience?
Yeah, very good question. So yeah, I forgot to mention, sorry about that. That those tools are presenting, they are most for Unix operating systems. But if you talk about JDK tools, CLI tools, those tools are all available on Windows as well, first of all. Second, for open file descriptors, for example, you will find a knowledge article on our support portal, which shows how you can, for example, check what files are open and calculate the number. You also have a netstat for Windows, which is similar to check open network connections. You probably don't have kill -3, which is a Unix thing, but you still can generate a thread dump. And the importance of tool I mentioned, one of very important here, and it works everywhere on any operating system, is JCMD with native memory tracking enabled. As I mentioned during the presentation, the problem that none of the visual tools like Visual VM, URKit, Eclipse, JConsole, for example, none of those report direct memory allocation. You can see that area used only enable native memory tracking, which by the way have a slight performance overhead. Oracle JDK reports about 7%. You can enable native memory tracking, and then you can use JCMD to actually check values. So hope this answers the question.
Thank you. We have another question on performance differences between a 0.1 versus a 1 vCore worker. So for not so high CPU intensive work, what sort of differences should people expect, or can they expect?
If it depends on the CPU utilization. If you deploy the same application, for example, and you observe, let's say, 5–10% max of CPU utilization on 0.1 or 1 vCore, you wouldn't see any problems. But if the rate of the messages or requests is too high, what can happen is that the queue of requests will start accumulating on 0.1, but because 0.1 has less memory, eventually you need more room to process. You need more room, you need to put more payloads in the memory, you need more memory, but you don't have it. So the memory reallocations due to defragmentation will start working intensively, and it may lead to performance degradation. But again, if you deploy the application with 5 requests per second with very simple response on hello world application, you probably won't find any difference between 1 record and 0.1.
And
it's a matter of capacity exercise and capacity planning. It's highly recommended because before going live, do an exercise and estimate what better suits your needs.
And from a user perspective, what sort of symptoms will they see on CloudHub if the worker is too small, from your experience?
The most obvious is an increased response time. When, for example, the CPU is burned, the increase in response time, and probably mule flow back pressure errors because the rate of the request, incoming request, has not changed, but the workload have become gradually slow. The responses like 503 might come back to the request. Something like this.
Thank you. You mentioned some queuing earlier where messages might be queued up for processing. The question was, what sort of queue are we talking about? Is there some sort of internal queue that a worker uses to process messages?
If you talk about VMQ, it's not, but there is a special mechanism and engine which is included. More information can be found under this link with reactive programming, which explains the mule4 threading profile. And I haven't mentioned it today because it's basically not debuggable, but HTTP listener has its own thread pool. It's a specific pool which is explained there, and it's managed by HTTP listener threads, let's say, execution engine.
There's no further questions. Is there any advice you would give as a key takeaway for the people listening in terms of performance and troubleshooting?
Yeah, so
especially working with support.
Yeah, first of all, don't be afraid to try something yourself. Try something which I presented today. I hope something was useful. And before raising a support ticket, please understand that we have many, many customers, thousands actually of those, maybe tens of thousands, not really aware. And we as support, we really want to help you, but we don't know your application. So consider talking to us from the point that we first time see the integration you implemented. Thus, providing some comprehensive package usually drastically reduces the time required to give you an assistance and help you toward the final resolution.
Cool. Thank you. I just wanted to give a wrap up. Thank you very much, Vitaly, for your presentation.
You're welcome.
The slides and the video will be available on the event page later today. So you can refer to that and any of the links that Vitaly has presented. If you're watching today, please submit the feedback form with your feedback on the session. It's always appreciated. And we look forward to having you join us at our next session. Thank you, Vitaly, and thank you all.
Thank you. See you later. Bye.